Hey, what's up, guys? So in this video, I will talk about one interesting idea in the additive combinatorics called the sidon set, and I will give you upper bound and lower bound. I think this is a very interesting topic, and but seldom video are there's almost no video on this topic. Okay, so let me just write down definition. So A is a subset of real number. And basically, you can define this over any abelian group. And A is called the sidon set if for all A, B, C, D in A, if we have A plus B equals to C plus D, this implies that this AB tuple is the same as CD tuple. Okay, so this means that, or simply speaking, if A plus B equals to C plus D, then you always have either A equals to C or B equals to D, or A equals to D, B equals to C. Okay, so basically this means that if you add any two numbers in this sidon set, then they are all unique. So yeah, okay. So maybe let me just write down example. So one famous example are like 1, 2, and 4, this kind of thing. And you can check that let's compute a sum set. So A plus A are all element B can be written as A plus B. Okay, so you have like let's say 1, 2, 4, right? So you have like 2, 3, 5, and sorry, 2, 3, 5, yeah, and then you have 3, 4, 6, and you have 4, 6, 8, and you only count you don't delete this, right? They are the same, right? Okay, so you total have like 2, 3, 5, 4, 6, 8. And then you can show, and obviously that these have three numbers, right? And then you have 6. Okay, and easy to see that this 6 comes out 3 times 4 divided by 2. So this means that every number can be written as A plus B can only uniquely factorize by decomposing into these two ways. So basically, this means that every sum like A plus B are unique. You can always find A and B in A such that A plus A equals to such that A plus B are uniquely determined by only two elements in A. Okay, so A is called a sidon set. Okay, so in this case, A is a sidon set. Okay, and okay, so this is definition. You can pause a video and think about this definition. So okay, and also let me just this set are also called B2 set. Okay, and one example which is not. Let me just write down a non-example, right? Let me just write down a non-example. So you can consider A to be like 1, 2, and 3, and now you can say I write a number, let's say 4, right? So 4 is in the sum set A plus A, right? But 4 can be written as 2 plus 2 or like 1 plus 3, right? So that means that 4 cannot uniquely decompose by in A plus A. The trivial decompose means that either exchanging 1 plus 3 or 3 plus 1. But in this case, that 4 has two different decomposition. Okay, so that means that this A is not a sidon set. Okay, so the simple question that one can ask is the following, right? So let's consider sidon subset A to be a subset of this n. Basically, this bracket n means that a set of 1 to n. Okay, simple question is that you ask what's the maximum number a sidon set can have. Okay, so simple question is you consider all the sidon subset of n, and you can define S of n or S of n to be the maximum number of sidon subset in n. Okay, you can fix n and you ask what's the maximum subset you can get to be a maximum, and also this set has restriction that this tend to be a sidon set. Okay, so now the question is that what's the upper bound and lower bound of this sidon set, right? It's probably not easy to see. Okay, so let me just write down notice. So notice that since A is a sidon, you can prove that the A subset A, the sum set size is basically A and A plus 1 divided by 2. Okay, and every this is simple to prove. You just write down a definition. Okay. Because every element can only can be factorized uniquely up to permutation. Okay, so that means that A plus A can achieve this bound. Okay, so let me just so the question is the upper bound of lower bound of this Sn. Okay, so let me just write down the simple fact. Okay, so 0 and 1 is that this Sn is lower bound. Upper bound is easy to achieve. Easy to prove. The trivial upper bound is 2 square root of A. Okay, and the proof is very simple. You just consider A plus A, as I said, right? It's basically A and A plus 1. Okay. Let me just denote A to be K. Okay. So in this case, these are distinct, right? These are distinct. So and also when these have all these are distinct number, right? All these are distinct number. But your A, right? Your A is a subset of 1 to n, right? 1 to n. 1 to n. So your A plus A, right? Your A plus A as a set must be a subset of 2 to like 2n plus 2n, right? So because you have too small. You have like n plus n, right? So your A plus A must be a subset from 2 to 2n. And these are 2n minus 1 number, right? So your A and A plus 1 divided by 2, these are all distinct number, must less or equal to 2n minus 1. Okay. So you always has k and k times k plus 1 divided by 2 is 2n minus 1, which is less than 2n. So this means that this is also greater than k squared divided by 2, right? So your k squared divided by 2 is less or equal to 2n. So k is less or equal to 2 square root of a. Okay, so this is the simple upper bound, right? Simple upper bound. Okay, so now we want to get a lower bound, right? Maybe some lower bound. So the lower bound is not hard to do, right? Because I need to like either construct a sidon set. Okay, so simple one example is that one can consider 1 to 4 eighths to be A. And it's easy to see that this must be a sidon set, right? So and then the S of n is greater or equal to log 2n. Okay, this is easy to see because you just only take the power of 2. Okay, and then they're all different. Okay, so these are simple lower bound that one can achieve. Okay, and another way one can prove, which is Erdős, what Erdős shows is the following. Basically Sn is greater or equal to n to the 1/3. Okay, so these has some bound here, omega of n to the 1/3. Okay, so this is like much more significant here. Okay, and the proof basically using the greedy algorithm. Okay, so the idea is that you can prove the following. Okay, so there's a simple lemma. Let's say if A is k and is less than n to the 1/3, then there is this x belongs to n, such that x cannot be written as A plus B minus C for all A, B, C belongs to A. Okay, so A is a subset either with size k and k is less than n to 1/3. Then there is this x. You can always find element in x in the 1 through n, such that x cannot be written as A plus B minus C. Okay, and if this statement is true, then you can define a new A prime defined to be A union x. Then A prime will be sidon, right? If A is sidon. Okay, so from this you can keep applying this lemma, then you prove that there's like k can. So if you do this, then basically you show that the Sn should be greater or equal to n to the 1/3. Okay, so this proof is just by counting. Okay, so proof counting. The counting lemma doing very simple, right? You just say so I can consider a set called A plus A minus A. Okay, so this set means that I count that all the element can be written as A plus B minus C. And since it's a tuple, right? So this guy is at most a to the cube, right? Because the simple bound is that every three of them are all different. So a plus b minus c is always different. Okay, so in this case, that this number is less than n. Right? So there's always x in n, such that x cannot be written as this. So the proof is done. Okay. Okay. And so now we achieve the following, right? To square root n, and it's 1/3. Okay. And so the question is that can we do better, right? So can we do better? Okay, I think the history is like the Singer, right? Singer find a sidon set, construct a sidon set, which satisfy the S of n greater than square root of n. So probably this is the best, I think. So basically, so the construction is difficult, and I will not talk about here, but you can construct sidon set which greater than square root n. So but I mean, there's still a factor of 2 here, right? So even though improve this. So the theorem that I'm going to finish in this video is that there's a proof that one can using more sophisticated analysis, one can show that S of n is less or equal to like the following, right? So square root n plus n1 divided by 4 plus 1. So this is the more sophisticated bound. Okay, more sophisticated bound. And in the rest of the video, I will finish this proof. Okay, and let's do this. Okay. So the proof. So basically, the goal is I will give some more sophisticated lower bound from this. Prove this. Okay. So that means that it almost match the upper bound and lower bound with only like n to the 1 to the 1 divided by 4 power. Okay. So the idea is that we want to order the element in A, right? So we want to sort the element in A. So element A in A. So let's say we have A1, let's say A2 up to A3 up to AK. Okay. And we can like doing this kind of separate. We can doing this kind of table. Okay. So I call order 1. So order 1 is basically means that only count the consecutive 1 difference. Okay. So let me just write out. So the order 1 element is basically A2 minus A1 and A3 minus A2 and A4 minus A3 up to AK minus 1. So all this element I call all this number I call order 1. Okay. Now I can define an idea called order 2. Basically, it's A3 minus A1, A4 minus A2. So all the 2 consecutive difference, right? And the A5 minus A3, up to AK minus 2. And I can define order L to be AL minus A1, sorry, AL plus 1 minus A1, and AL plus 2 minus A2, up to like AK minus L. Okay, so this is the order L. Okay, and very simple exercise is if you can sum, right? You can sum over this, sum over all the elements. You can see they're all cancelled, right? So these are AK minus A1. And for this one, that you can see that the A3 and A4 were cancelled. So the remaining is A1, A2, and the ended remaining is AK and AK minus 1, right? So you get AK plus AK minus 1 minus A1, A2. Okay. And for this one, that basically you can easily prove, right? It's AK minus 1, up to AK minus L minus 1 minus A1, A2 up to AL. Okay, so these are some of it. Okay, so I can do this labeling. Okay. Okay, so now since A is sidon, right? So I know that A is sidon. So I know that all these different are distinct. Okay, so that means that AJ minus AI is always different from AJ prime minus AI prime. Okay, this is trivial, right? Otherwise, that if there's an equal sign, then AI plus AI prime will equals to AJ plus AJ prime. But then this violates the conditional sidon set. Okay, since they're all different, so I can guarantee that all these they are different. They're all different. Okay, so now I can do the following. I can sum over all the L order difference. So basically, I sum over the following. I do AJ minus AI, and so I have 1 to J up to K, but I only care about J minus I less or equal to L. Okay, so I sum all the element. I sum all the element of this table. Okay, I sum this. Basically, I sum all of this. Okay. Now these are all different, right? So these are all different. So they must be greater or equal to 1 plus 2 up to L, right? 1 plus 2 up to the sides. Okay. So this guy must be equal to 1 plus 2 up to something, right? Up to something. And so there are, let me just count, right? So there are k minus 1 element here, and then there are k minus 2 element here, and then there are k minus L element here. Okay, so the total element in this table will be k minus 1 plus k minus 2 up to k minus L. Okay, right? Because you just count how many number you have. And this will equals to it seems very simple, right? Just L and k minus L plus 1 divided by 2. Just arithmetic progression. Okay, so this we just put numbers here. So these are like L and k minus 1 L plus 1 divided by 2. Okay, so what you have is the following. You can get the following you get 1 plus 2 up to L, k minus half of L plus 1. This will less or equal to this guy. And then this guy is basically another arithmetic progression. So you can sum over them. Then you can prove that it's greater or equal to L half L squared, k minus L plus 1 divided by 2 squared. Okay, so this is just seems this inequality is just trivial. Okay. So get the following this. Okay, so now we have lower bound of this different, and we can find upper bound, right? So we go less or equal to. So now let's see, right? So this sum is bounded by what? Bounded by 2n, right? Because it's bounded by n, right? Because the either AK is n or A1 is 1, right? So it's bounded by n, and this term is bounded by 2n, right? Because this is n and n minus 1. This is probably the largest one. And then this guy is bounded by ln, right? So I can sum over this L. I can sum over this term. So I get the trivial upper bound, which is n plus 2n up to like ln. Okay, so this is half of LL plus 1n. Okay, so now I get this following inequality. This one, then this one. Okay, so let me just write down. So what we have is half of L squared, k minus half of L plus 1 squared, less or equal to L plus 1n. Actually, you can show that it's definitely not equal. Okay, if you do this, then you can show that k is less or equal to square root of n plus square root of n divided by 2L plus L plus divided by 2 plus half. Okay, and the reason is that if you just do the computation for this, then you can show that k minus, you just take a square root of 2, right? You just take a square root of 2. So you get k minus L plus 1 half less or equal to square root of n times L plus 1 divided by L. Sorry, it's n of L plus 1 divided by L. Okay, and you can use 1 plus x, take a square root less or equal to 1 plus x divided by 2. Okay, so this is just Taylor series. Okay, so you can achieve this. So your k will less than square root of n plus square root of n divided by 2L plus L divided by 2 plus half. And then, so you just pick L, right? So let me just pick L to be n divided by 1 to the 4th. So your k will less than square root of n plus n divided by this 1 to the 4th, right? Plus half. Okay, so this gives you the much sharper, much closer upper bound for this essay. Okay, so now we can achieve this by half. Okay, so there's a next time in the future I will give you the construction of this sidon set. But basically now we already achieved this kind of this kind of upper bound and lower bound from this sidon set.